So I'll be sharing my screen. So can you see this PPT? Hello.
Yes, sir.
Right. So this is what we are discussing now. So these are the topics, main topics. Okay. So we are going to discuss basic concepts, type of graphs, subgraphs, isomorphism, connectivity, trees and its properties, types of trees, and Eulerian graphs, Hamiltonian graphs, planar graphs, and the four-color problem. Okay. So we discussed about graph definition. Okay, but I could not write down that clearly in the last class. So what is a definition of a graph? What do you mean by graph? Graph consisting of set of vertices and set of edges, right? And where V is non-empty set and E can be any set, okay, such that, and there is no commonality between E and V, okay, because set theoretical point of view, elements of V are entirely different from elements of E, such that there is a function psi g, okay, which is mapping from this edge set, which is mapping from edge set to uh, V cross V, or V and V, I said V and V, okay. So if it is V cross V, if the range is subset of V cross V, that is a directed graph. If the range is subset of V and V, that is called an undirected graph, I said. Okay, so that is what we have seen in the earlier class. Okay, so here we have denoted these things in terms of ordered pairs. Therefore, you have seen directions. Okay, there is an edge from 1 to 2. Okay, that's a directed edge, because, and there is an edge from 1 to 1, that is called a loop. Okay, if there is more than one edge between the two vertices, they are called multiple edges. Okay, so for an undirected graph, we uh, uh, map edges with sets. Okay, for directed graphs, we map edges with the ordered pairs. That is the only difference. Okay, so for a directed graph, there is an edge from 4 to 3, but there is no edge from 3 to 4. Okay, whereas whereas undirected graph, there is an edge from 4 to 3, there is an edge from 3 to 4. Okay, so if there is an edge between two vertices, we say that the edge is incident with the vertices, or the vertices are also incident with edges, vice versa. Okay, so in this case, edge D is incident with 3, edge D is incident with 4, or you can say 4 is incident with D, and the vertex 3 also incident with D. Okay, so elements of the V are called vertices or nodes, and elements of E are called edges or links. Okay, so mostly we'll be discussing undirected graphs only. Okay, and we discussed about what is called adjacency matrix and what is called incidency matrix, and what is this called adjacency matrix, right? Adjacency matrix. So how adjacency matrix is defined? So A equal to Aij, right? Elements of matrix are Aij of order n by n. What is n refers to? N refers to the number of vertices, right? N refers to the number of vertices. And how Aij is defined? Aij equal to the number of edges. The number of edges. Okay, edges between Vi and Vj, with loops counted twice. Loops counted twice. Okay, so using this definition, we have seen the adjacency matrix. In this case, 1 to 1 there is a loop, therefore that loop is counted as 2, and 1 to 2 there are two edges, so we have written 2. and 1 2 3 there is no edge, 0. 1 2 4 there is no edge, so 0. Similarly 2 2 2, 2 to 1, 2 to 1 there are two edges, okay. 2 to 2 there is no loop, 0. 2 to 3 there is no edge, 0. 2 to 4 there is one edge, so we have written 1. Similarly 3 to 1 there is no edge, 0. So 3 to 2 there is no edge, 3 to 3 there is no edge, 3 to 4 there is an edge, okay. Similarly 4 to 0, 4 to 1, 4 to 1 there is no edge, 0. 4 to 2, 4 to 2 there is only one edge, so 1. And 4 to 3 there is only one edge, and 4 to 3, 4 to 4 there is no loop, therefore 0, okay. So now you can see it as a symmetric matrix, okay. It is a symmetric matrix, and each row sum is equal to the degree of that vertex, okay. And what do you mean by degree? For an undirected graph, degree is nothing but the number of edges that are going that is going from the vertex, okay. If it is a loop has to be counted as 2, okay. So for this vertex the degree is 1 2, loop is 2, 2 plus 2 is 4, okay. So 2 plus 2 is 4. And what is the degree of the vertex 2? So 1 2 3 there are so degree of the vertex is 2, degree of the vertex is 3, so you can see that that is row sum is also 3, and so on. Degree of the vertex is 1, row sum is 1. Degree of the vertex is 2, you can see row sum is also 2, okay. Whereas for a directed graph there is a concept called in degree and out degree. There is nothing like degree, in degree and out degree, okay. What is out degree? Which is going away from the edges, from the vertex, that is denoted with out degree. So out degree of 4 is 1, there is no in degree, so in degree of 4 is 0. And in degree of 3 is 1, there is no out degree, okay. And here in degree of 2 is 1, out degree of 1 is also 1, like that. Is it clear? Can I proceed?
Yes, sir.
Right. Similarly, we discussed about incidence matrix also. So what is incidence matrix? Incidence matrix is a matrix B. Incidence matrix is a matrix B. And what is the definition of matrix B? What is the order of this matrix B? It is of order Bij, of order number of edges by number of vertices by number of edges. So what is n denotes? Order of the vertex set, and m is the order of the edge set, okay. Then how Bij is denoted? Bij is defined as, okay, 0 0 if Vi is not incident with Vj. The vertex Vi is not incident with Ej, that is denoted with 0. Similarly, if it is 1, if Vi is incident with Ej, okay. And what is 2? If Vi is incident with Ej and Ej is a loop, okay. And in this case Ej is not a loop, okay. So in that case you can see here okay, these are all vertices. Vertices are denoted 1 2 3 4, edges are denoted with ABCD, okay. So you can see one is incident with A, because it is a loop I have written as 2, and vertex 1 is incident with B, therefore it is 1. Vertex 1 is incident with C also, this is C edge, therefore 1, okay. Vertex 1 is not incident with D is here, okay. Vertex 1 is not incident with D, therefore it is 0. Vertex 1 is incident with E, E is this part, okay. E is this one, edge connecting 2 and 4 is uh, this one, so let me call here, okay. So that is also 0. Similarly, 2 is 2 incident with A, 2 is not incident with A, so 0. Is 2 incident with B? Yes, so 1. Is 2 incident with C? Yes, 1. Is 2 incident with D? D is here, 0. 2 incident with E, 2 is incident with E, therefore 1. Similarly for 3 is incident with not incident with A, 0. 3 is not incident with B, 0. 3 is not incident with C, 0. 3 is not incident. 3 is incident with D, therefore 1, and 3 is not incident with E, therefore 0. Similarly 4 incident with A, no, 0. 4 incident with B, no, 0. 4 incident with C, no, 0. 4 incident with D, yes, 1, and 4 incident with E, 1. Okay, so that is how we write down the incidency matrix. Okay, so in the incidency matrix you can see sum of each column is 2. And how do you get the degree? By adding the row. 2 plus 1 plus 1, 4. Degree of 1 is 4. 1 plus 1 plus 1, 3. Degree of 1 is 3. Degree of the vertex 2 is 3. Okay, for 3, 1. For 4, 2. You can see. Okay, so is this clear how to write down incidence matrix and adjacency matrices?
Sir, the values for an incidency matrix, they can only be 2, 0 or 1.
Yes.
But for adjacency matrix, they can be more, no, sir?
Yeah, because it depends on the number of edges, right?
Okay, sir.
If there are 100 edges between 1 and 2, then I have to write it as 100 only.
Got it, sir.
Okay, right. So, so that's about incidency matrix and adjacency matrix. Shall I proceed?
Yes, sir.
Okay, so we have defined what is graph. Okay, so graph is nothing but some people call the graph as an ordered pair like this. Okay, so many people write the graph as like this: G equal to V comma E. So one way of representing is like this: G equal to V comma E, and other people call this as an structure V okay, E and psi G, because we are mentioning the mapping also, no? So they will call more precisely they will denote the graph like this. Okay, so after that okay, so so if there is an edge between U and V, if there is an edge between U and V, we say that U and V are adjacent vertices. Okay, if there is an edge connecting U and V, we say uh, adjacent vertices. U and V are said to be adjacent vertices. In case of a directed graph, arrows will be there, and in case of undirected graph, you will see just line. Okay, and what is a loop? An edge connecting a vertex to itself is called a loop. What are multiple edges? If there are more edges, more than one edge connecting, joining two vertices, then they are called multiple edges. And what is simple graph? A graph without loops and multiple edges. A graph without loops and multiple edges is said to be a simple graph. Okay, so mostly our discussion is going to be simple and undirected graph only. Simple and undirected graph. And you can see this is an example of a simple graph. Okay, and which is undirected. You can see there are no arrows. Why it is simple? There are no loops. You don't see any loop at any vertex, and there are no multiple edges. There are no multiple edges between U and V. Okay, between U and V there is one and only one edge, if at all there is an edge. Okay, so this kind of graphs mostly will be considering unless otherwise mentioned. So whenever I say graph, you can think of as an undirected graph and simple graph. If there is a need, I will specify particularly. Okay, so this is another example of a simple graph, and this is called NCube. I think this is a very much important graph in your computer science point of view. Okay, so what is binary strings, right? 0 0 0 0 0 1 0 1 1 1 0 0. Okay, so how many strings, binary strings you will get? how many strings containing 0 and 1 of length 2?
4.
4. Okay. Of length 3?
8.
8. Okay. So you know those strings. So okay, 0 0 0 1 1 0 1 1. If it is 8, it is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1. Okay, 1 2 3 4 5 6 7 8. Okay, and what is NCube? NCube, you give an edge if there is a difference between two strings with at most 1 bit. Okay, if there is a difference between the corresponding bits is at most 1, then join those two vertices. Okay, in case of two vertices, only 0 and 1 single edge. In case of these two, you see 1 0 0 0 0 0 is same, but at this position 0 1 are changed. Okay, how many difference? Only one difference in the position. Okay, so you connect these two. Similarly, okay, you see these two 1 0 1 1 1 1 position is same, whereas 0 1 position is changed. Okay, so such that there is only one difference. So therefore these two are connected. Similarly, 1 1 and 0 1 1 1 position are same, there is only one change in the position, so in the second stage. Okay, therefore you connect these two. Okay, similarly you connect these two. Okay, so like that, if you give edges like that, the graph so formed is called uh, an NCube. Okay, similarly you can construct NCube for strings of length 3 also. Okay, so you try to construct and tell me how that looks like. Okay, that means you have to connect edges. Okay, you just see this example. Which two I can connect? Can I connect these two?
Yes, sir.
Can
Yes.
I connect these two?
Yes, sir.
Yes, sir.
Can I connect these two?
No, sir.
How
Two
many
bits
changes are
difference.
there?
No.
One change,
Two
two
things.
change. So I said there should be one and only one such change. Therefore these two are not connected. Is that okay? So you connect the vertices by satisfying this property and tell me what kind of graph you are going to get. Okay. If there is a string with n, if there is a string of length n having zeros and ones, okay, the graph that is so obtained is called hypercube. Okay, that is so obtained is called hypercube. Okay, so multigraph we have seen, because if there are multiple edges, we may call it as a multigraph. These are all called
Sir, can you
parallel edges.
repeat about hypercube, sir?
Graph obtained by joining the strings of length n. This is length 2, no? Similarly, you can get a graph by joining the strings of length 3. You can similarly get a graph by joining the strings of length 4. You can get a graph by joining the strings of length 10. So those graphs are called hypercubes. Okay. This is also a hypercube. This is also hypercube. I'm telling about the generalized version. Okay. So this is a directed graph. You can see arrows are there. Therefore, we are denoting with this with ordered pairs. Okay. There is an edge from U to V. Therefore, ordered pair U comma V. Okay. There is an
Excuse me,
edge.
sir.
Tell me.
Sir, can we draw an edge from 000 to 010? There is only one number
Here. Tell me. 0
difference. 0 0
0 0.
0
Hmm.
to 010.
Yeah. How many changes are there? These two are same. These two are same. There is only one change, one state change from 0 to 1, right? Therefore, you can give an
Yes,
edge
sir.
from 0 0 0 to 0 1 0. You can give
Okay,
a edge between these two vertices.
Okay.
Is that okay?
So
Right. So here you can see there is an edge from U to V, therefore ordered pair U comma V, and V to W there is an edge, so ordered pair V to W. There is an edge from V to W, therefore ordered pair W comma V. Okay, so a directed graph will be denoted with a set of ordered pairs in the edge set. Okay, so you may call this as some A, edge A. You may call this as edge B. You may call this as edge C. That means A equal to ordered pair U comma V, B equal to ordered pair V comma W, C equal to ordered pair W comma W. Okay, and degrees of the vertex we denote with D of V or DEG of V. Okay, if there is no degree, okay, if the no edge is incident with the vertex, then that is called isolated vertex. Okay, see here there is no edge is incident with this vertex, therefore K is isolated. And if the degree of the vertex is only one, then that is called pendant vertex. Okay, so these two are pendant vertices, and this is an isolated vertex, and this is not. This is just a vertex. Okay, and what is the degree sequence? Degree sequence is nothing but if you are writing the degrees of the vertices in an order, that is called degree sequence. Okay, so in this case, if I draw like this, okay, so okay, if I draw like this, if I draw so if this is a graph like this, let us say this is V1, let us say V2, let us say V3, V4. Okay, so what is the degree sequence? Degree sequence means I said okay, writing the degrees in an order: degree of V1, degree of V2, degree of V3, and degree of V4. That means what is the degree of V1? Degree of V1 is 2. Okay, degree of V2 is 1. Degree of V3 is 1. Degree of V4 is 0. So this is called a degree sequence. This is called a degree sequence of the graph. Okay. And okay, as I said, out degree and in degree. In degree is denoted with minus, degree minus, and out degree is denoted with degree plus. Okay, for U out degree is 1. Out degree is 1 plus 1, 2. Okay, there is no in degree. And for V, in degree is 1, out degree is 1. For W, in degree is 2, there is no out degree. And what is the theorem on graphs? For a graph, undirected graph. Okay, if you take sum of all the degrees, that will be equal to the 2 times number of edges. Sum of degrees of all vertices is equal to 2 times the number of edges. You can see here how many. What is the sum of what is the degree sum? Equal to 2 plus 1 plus 1 plus 1 equal to how much? Sorry, 2 plus 1 plus 1 only. So what is this sum? This is equal to 4, and this is equal to 2 times the number of edges. How many edges are there? 2. 2 into 2 is 4. Okay. So because each degree is contributing, each edge is contributing a degree to one vertex. Each edge is contributing degrees to its adjacent vertices. Therefore, if you take sum of all those degrees, that will be equal to the 2 times the number of edges. That means to say that what? Sum of all degrees cannot be odd, because 2 times any number is always even. So sum of all degrees of vertices is always even. And there is one more important theorem called this one. in an undirected graph, okay, it will the number of vertices of odd degree is always even. In an undirected graph has even number of vertices with odd degree. Okay, you count the number of vertices of odd degree, that is always even in an undirected graph. That means you cannot have a odd number of vertices of odd degree. Okay, you only will have even number of vertices of odd degree. Again, you can see here how many are there of odd degree. One is odd degree, one is odd degree. What is this? 2. 2 is even. Similarly, you can select, you can write like this also. In this case also, what is the degree of 1? 1, 2, 2. 1, 2, 2. What is the degree of V3? 3. 1, 2, 3, 3. What is the degree of V4? 1. So how many, so how many odd degree vertices are there? Only 2. It is even. Even if you add one more. If that is the case, this becomes 2, this becomes 1. Okay, so you cannot have odd number of vertices of odd degree. The number of odd degree vertices is always even. That is an important theorem in graph. Is this clear?
Yes, sir.
Right. So next one. Okay. In case of a directed graph, okay, sum of out degree is equal to sum of the in degree, which is equal to the number of edges. Okay, so you can count the number of edges through sum of in degree or through the sum of out degree. And we have seen this one, incidence matrix and adjacency matrix. Okay, so this is another example of writing adjacency matrix, incidency matrix. Okay, this is another example. Okay, so next, what is graph isomorphism? What do you mean by graph isomorphism? When do you say two matrices, two graphs are isomorphic? Two graphs are isomorphic. Okay, so right here, graph isomorphism. Graph isomorphism. Let us say you have a graph G. Let us say V comma E. Okay, let us say you have another graph. Let us say G dash, V dash comma E dash. These two are two graphs. Okay, so if I want to say G is isomorphic with G dash, if I want to say G is isomorphic with G dash, okay, you should have two mappings. Okay, there should exist a bijective function. There exists a bijective function f from V to V dash. What do you mean by bijective mapping? Do you remember? What is bijective?
Mapping from domain as well as codomain.
That is a function that is called mapping. When do you say mapping is called bijective mapping?
When it is 1, 1 and on 2.
1, 1 and on 2. What do you mean by 1, 1? Distinct elements of A should have distinct images. That means no two elements should have same image. And what do you mean by on 2? No element in the codomain should have a every element in the codomain should have a pre-image, right? That means no element in the codomain is left out. So that means there should be a 1, 1 correspondence between elements of V and elements of V dash. And second condition is there should exist a bijection from the edge set of first graph to edge set of second graph. Okay, and what is the third condition? Okay, so if you are saying that so let us say this is xi g. Okay, so the corresponding okay, let us say, so let us say you take an element E, okay, which is incident with U and V. belongs to E first set such that E equal to UV. Okay, UV, I mean to say that there is a edge E is connecting U and V, or edge E is incident with the vertices U and V. If that is the case, then you will have image, no? Because U and V are vertices. Vertices are elements of V. Okay, then you will have an image. You will have an image. What is that image? F of U. And V will have an image. What is that? F of V. Okay, and F of U and F of V must be connected by the image of E. That means what? What is the image of this one? G of E. G of. Okay, so whenever an edge is incident with the U and V, okay, its image is also should incident with the corresponding images of the adjacent vertices. Is that okay? So if that is the case, and what is G of E? G of E is nothing but G of UV. Okay, E is nothing but UV, no? So G of UV equal to F of U, F of. Okay, if that is the case, we say those two are isomorphic. Okay, and the function, okay, the function and the association between G and G dash is said to be isomorphism. Okay, that association is nothing but a function. So I'll just write one example and tell me whether there exists an isomorphism between those two graphs or not. Okay, so I'm going to draw a graph. So what you have to do is basically you have to map vertices of first graph to vertices of the second graph. You have to map the edges of the first graph to edges of the second graph, and such that whenever you take an edge which is incident with you, their images are also incident with the corresponding images of the vertices. Okay, so I'm going to draw two graphs. Okay, so first graph is like this. So let us say there are four vertices. Okay, 1, 2, 3, 4. Okay, so let me call this as so draw a I'll draw like this. So let me call this as 1, 2, 3, 4. Four vertices. I am naming those vertices with 1, 2, 3, 4. Okay, so I'm drawing edges now. 1 to 2. There is one edge. Okay, there is 1 to 2. There is another edge also. Okay, it's a multi-graph. So this edge I am denoting with alpha. This edge I am denoting with beta. 2 to 3, there is an edge. I'm calling it as gamma. And 3 to 4, I'm denoting with delta. Okay. Now I'm drawing one more graph. Okay. So like this, I'm calling it as A. This vertex I'm calling it as A, B, C, D. Okay. So there is a edge from A to B. There is an edge from A to B. I'm calling it as X. There is an edge from B to C. I'm calling it as Y. There are two edges from C to D. Okay. One is say Z, other one is call it as W. Okay. So this is Z. Let me call it as W. Okay. So can you establish isomorphism between these two graphs? Let me call it as G1. Let me call it as G2. Okay. Can you give an association?
Yes, sir.
Please give them association. How do you map vertices of one set to vertices of another set? Let us say F. What is F of 1? 1 you want to map to which vertex?
D, sir.
D, yeah? You want to map this to D. Okay. Next vertex 2. 2 you want to map to
C, sir.
C.
C. Next vertex 3, you want to map to
B.
B.
B,
B.
sir.
Vertex 4, you want to map to
A.
A.
A. Okay. Now how do you map edge set? Alpha you want to map to
W.
W, and beta you want to map to
Z.
Z, and gamma you want to map to
Y.
Y.
Y, and delta you want to map to
X.
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 Okay. Now you take any edge. Okay. Now what is that image corresponding to the this one? Let me take randomly check. So let me take this beta. Okay. What is beta? Beta is equal to 1 comma 2. Am I right? Beta is connecting 1 and 2. What about beta image Z? Okay. Is this Z connecting to image of 1 and image of 2? What is image of 1? D.
D.
What is image of 2? C. Is
C.
this Z connecting D and C? Then Z connecting D and C. Am I right?
Yes, sir.
So like that, that should happen for every edge. That should happen for every edge. If that is the case, we say that these two are isomorphic. Okay, so you can check that whatever the edge you take, it is satisfying those properties. Okay, so therefore it is an isomorphism. Okay, now instead of this, if I draw, let me draw one more graph. Okay, I'll call that here G2. I'll draw one more graph. Okay, I'll draw here. So 1, 2 like this. Okay, so let me call it as 1, 2, 3, 4. Let me call it as A, B, C, D. Now just write down this in your book and see if you can establish any isomorphism between these two. Call this as G1. Call this as G2. Can you? This is looking similar, but such isomorphism exist. Please see.
No, sir.
No, sir.
You try to map and see. Okay, don't just.
Sir, can't we directly say isomorphism doesn't exist by saying that here one node has two edges and like B has two edges, D has two edges, and C has three edges, A has one. So 1, 2, 2, 3.
That means
And here
write down the degree sequence. That your observation is very good. What is the degree sequence of this?
1, sir.
1. What is the second degree sequence?
3.
3. What is the next one?
3.
3. What is the next one?
1.
1. What about this? 1.
1, 2, 3, 2.
1, 2, 3.
2.
You can see 1, 1 is there. 3, 3 is there. But these two are not matching. Right?
Yes, sir.
So when the degree sequences are different, they cannot be isomorphic. You cannot establish the isomorphism. Is that okay?
Yes, sir.
And converse need not be true. If the degree sequence are same, may exist, may not exist. But if they are not equal, definitely does not exist. Okay. So in this case, if you see the degree sequences, what is the degree sequence of 1? 3. I think this is 2. Sorry. Where is this? What is the degree sequence here? 1 degree is 2, 2 degrees 1, 2, 3, 3, 3 degree is 2, and 4 degree is 1. And what is the degree sequence of A? A is 1, and this is 2, and this is 3, and this is 2. Okay, so 2, 2, 3, 3, 2, 2, 1, 1. Is it clear?
Yes, sir.
Okay, now write a question. Okay, in your notes, draw all non-isomorphic graphs with vertices 4. Draw all non-isomorphic graphs of with vertices 4. So this is one graph. Do you agree? What is the degree sequence of this graph?
0, 0, 0, 0.
Am I right? Now I can draw a graph which is not isomorphic with this. I just put an edge. You call this as V1, V2, V3, V4. Now I am definitely sure that these two are not isomorphic. What is the degree sequence? 0, 0, 1, 1, or you can say 1, 1, 0, 0. Doesn't matter. It depends upon what name you are giving. If you are giving like this V1, V2, V3, V4, then the degree sequence must be 1, 1,
1 1.
0, 0. Is that okay? Because the degree sequences are different. Okay, these two are non-isomorphic. Similarly, you can draw one more graph with a different degree sequence. When there is a different degree sequence, definitely those two are not isomorphic. Is that okay? So try to try to draw the graphs of all non-isomorphic graphs with 4 vertices. Did you copy? Question is, draw all non-isomorphic graphs containing 4 vertices. Shall I proceed?
Yes, sir.
Draw all non-isomorphic simple graphs. Because if it is not simple, you can add n number of edges, right, in between two vertices. Then there is no never-ending process. That's an infinite. So draw all non-isomorphic simple graphs with 4 vertices. Shall I proceed?
Yes, sir.
So after that, okay. So this is another example. Okay, you can give an association such that those two are isomorphic. You can see that degree sequence will be same. What is the degree sequence of this? 2, 2, 2, 2. What is the degree sequence of this? 2, V1 is 2, V2 is 2, V3 is 2, V4 is also 2. Okay, so these two are isomorphic. These two are isomorphic. These two are isomorphic only after establishing a relation like this. Okay, you should associate vertices of first graph to vertices of another graph. You should associate edges of first graph with edges of second graph. And when I say bijection, that means the number of vertices must be same in both the graphs. If the number of vertices are different, then obviously they are not isomorphic. If the number of edges are different in two graphs, obviously it will not be isomorphic, because biject 2 means what? Both for finite sets, both will have same number of elements. Is it clear? Okay, so what do you mean by subgraph? You just delete some edges or some vertices. The resultant graph is a subgraph. Okay, that means when you delete some vertices, that means the resultant vertex set is a subset of the original subset. That means V dash will be a subset of V. And if you delete some edges, you can delete 0 edges also. That means every graph is a subgraph of itself. Okay, so if you delete some edges, then the resultant edge set will be a subset of original edge set, such that, okay, if there is an edge in E dash which is incident with the two vertices, those two vertices must belong to V dash. Okay, okay, and the same edge must be there in here also. Okay, so broadly telling, if this is obtained from the original graph by deleting few vertices or some few edges, that is called a subgraph. You can see this edge is deleted, so this is a subgraph, and u comma v, two edges and one vertex is deleted, uv, this is one subgraph. Like that you can generate several subgraphs from a given graph. Is that okay?
Yes, sir.
Okay, so subgraph is over. Okay, and what do you mean by spanning subgraph? When do you say a subgraph is a spanning subgraph of the original graph? If both are containing the same vertices, if both are containing the same number of vertices, then they are said to be spanning subgraph. So in this, which one is a spanning subgraph of the original graph?
H1, sir.
H1, because H1 containing same vertices as of G, therefore it is called spanning subgraph. Okay. And what do you mean by graph induced subgraph? If the edge set, okay, a subgraph is said to be an induced subgraph if both are having the same edges. Okay, edges of G is same as edges of E, then they are said to be then it is said to be induced subgraph. That means V dash can contain less number of vertices than V, but the number of edges must be same. That is said to be an induced subgraph. What is an example? Let us say like this. Okay, so V1, V2, V3, V4, V5. So my graph containing 5 vertices. How many edges are there? 4 edges. Okay, so if I draw like this is containing all the edges of G. So if I call this as G, this as H, is it not induced subgraph of G?
Yes,
Both are
sir.
containing same edges. Is that okay? So that is an example of an induced subgraph. And what is a complete graph? If every distinct pair of elements are adjacent. What do you mean by adjacent? If there is an edge between two vertices, then those two are said to be adjacent. Okay, if like that, every pair of distinct, if every distinct pair of vertices are adjacent, that means if there is an edge between any two distinct vertices, then that is said to be complete graph. Okay, so that they are denoted with Kn. Okay, Kn is a complete graph with n vertices. What is K1? Okay, this is only one vertex, because I am telling it as a simple graph. Loop is not allowed. Okay, so this itself can be called as a complete graph with one vertex. So for K1 there is no edge. For K2 there are two vertices and there is an edge connecting these two. So this is a connected graph. And for three vertices there is an edge from V1 to V2, V2 to V3, V3 to V1. So you take any two vertices, they are connected. It's not connected, they are adjacent. I should not use the word connected because there is another definition for connected. So any two vertices are adjacent, therefore it is a complete graph. You can see a graph with 4 vertices. You take any two vertices, you take any two vertices, they are adjacent because there is an edge between any distinct pair of vertices. Therefore this is an example of a K4. Similarly you can draw K5, K6, K7 like that. Is that okay? Shall I proceed?
Yes, sir.
Right. Okay, so what about connectivity? Okay, so what is walk? What is trial? What is path? What is cycle? So these things we have to see. Okay, so what is a walk? I will write here. Okay, so what is a walk? Walk is a sequence of vertices and edges. Sequence of vertices and edges like V0, E1, V1, E2, okay, V2, E3, V4, oh sorry, E3, E4, V4, like that. Okay, I'm not telling E1, E2, E3 are distinct. I'm not telling V1, V2, V3, V4 are distinct. Okay, vertices may be distinct, edges vertices may be repeated, these edges may be repeated. Only condition is if you are writing an edge here, this should incident with the V2 and V3. This should incident with the V2 and V3. Such a sequence is said to be a walk from, like that. If you are having like this Vn, walk from V0 to Vn, walk from V0 to Vn. Okay, so if you draw some something like this, okay, let us say this is V1, V2, okay, V3, V4, let us say V5. Let me call this as edge E1, E2, E3, E4, E5, E6. Okay, so just like you traverse from one node to another node. Okay, and in that whatever you is coming across, you write that in a sequence. Okay, so let us say we are starting from V1. Okay, so V1, I'm walking along E1, let us say E1. Then E1 I will write. E1 is connecting to what? V2. From V2 I'm going along, let us say, let me draw like this also. So let us say from V1, V2 I'm going to V3. Okay, so how I'm going along V5? That means E5. Okay, and I'm reaching to V3. V3. From V3 I'm going to V1. How? E3. Okay, and E3 is connecting to V1. Again V1 to V2 I'm going E1. Okay, because E1 is connecting to V2, V2. Okay, now V2 I'm going to V4. How did I give a name to this?
Along V3, sir.
This one. E1, E2,
E7, sir.
it should be
E7.
E7, right? So it should be E7.
Yes, sir.
E7. So from V2 to E7, and E7 is going to V4. Okay, so this is a walk. This is a walk from where to where? This is a walk from V1 to V4. There can be several walks from V1 to V4. I made one walk in which some of the vertices are in which some of the vertices may be same, some of the edges also may be same. Is it clear? Okay, this is called a walk. When this walk is said to be closed walk,
If it's V1 to V1, sir.
if the initial vertex is equal to the terminal vertex, then that is said to be a closed walk. Am I right? So from V4, if I am trying going back to V1, okay, so that means E2 and V1. Okay, so from here to here, if I am writing the walk like this, initial equal to terminal, that is a closed walk. Or if I am writing only this part, if I am writing the walk as like this, then this is also called as a walk. So there can be several walks from one vertex to another vertex, and there can be several closed walks from one vertex to itself. Is that clear? Okay, so walk. So this is walk, and other one is closed walk. What is simple closed? What is another what is an example of a closed work? I can write it as a simple. Let me write V1, E1, V2, E7, V4, E7, V4, E2, and V1. This is an example of a closed work. Is it okay? So then, what is a trial? Okay, if all okay. So what is trial? Trial is a walk. Trial is a walk in which all the edges are distinct. Trial is a walk in which all the edges are distinct. Vertices may repeat. Vertices may repeat, but the edges must be different. Okay. So can this be called as a trial? E1, E7, E2. All the edges are distinct in this walk. So this can be called as a trial. In fact, it can be called as a closed trial because initial vertex is equal to terminal vertex. And what about this E1, E1? You can see E1, E1 are repeating. Therefore, this is a walk. This is a walk, but not a
Trail.
trial. And if I write like this, V1, E1, V2, E7, V4. What about this?
Trial.
Okay. V4. Okay. So this is a trial because edges are also different. Okay. So this is called a trial, and this is called a closed trial. This is called a closed trial. Okay. So then what is path? So what in a trial? What is the observation? All edges. Sorry.
Distinct.
Edges are distinct. Now, what do you mean by path? What do you mean by path? If all the vertices are also distinct, if all the vertices are also distinct, okay, then that is said to be path. Okay, in this case, you see vertex V1 appearing 2 times. Okay, therefore this is a walk, but this cannot be called as a path, not a path. Okay, so this is neither path nor a trial. Okay, so how can you give a path? Can I give a path like this? V1, E1, V2, E5, V3. Okay, V3, E4, V4. And do you agree that if the vertices are all distinct, then edges are also distinct? Can you have a graph with repeated edges but non-repeated vertices? Can you have like that? So when I say graph is having distinct vertices, automatically it will have distinct edges. Okay, so this is an example of a path, okay, in which vertices are distinct are also edges are all distinct. So this is a path. And when this path is said to be a cycle, if initial is equal to the terminal, okay, if initial is equal to the terminal point, that is said to be a closed path or a cycle. Closed path or a cycle. So what is an example of a closed cycle? In this case, can I give a cycle with V1, E1, V1, E1, V2, E7, V4, E2, E2 and V1, is it a cycle? It is a path. It is a closed path. Okay. Initial vertex equal to terminal vertex. So this is a closed walk. It is a closed walk in which vertices are distinct and hence edges are also distinct. Therefore, it is a cycle. Is that okay?
Sir, here V1 are repeating, no sir. So
Where?
how can be?
Except initial and terminal, I said. Okay.
Okay,
A
sir.
path is said to be a closed path. Closed path means what? Except initial and terminal, all the remaining edges are all the remaining vertices are distinct. Okay. So that is said to be a cycle. Now this cycle can be classified as two types: even cycle and odd cycle. Okay. What is even cycle? What is odd cycle? Okay. What do you mean by length of the path? Length of the path is the number of edges that are there in the walk. Okay. That are there in the path. That is called the length of the path. In this case, 1, 2, 3, 3 edges are there. Therefore, length of the path is 3. So here the length of the cycle is 3 edges. Okay. So what do you mean by even cycle? And what do you mean by odd cycle? These two are examples of cycles, right? So what is the length of the cycle? Call this as G1. Call this as G2. What is length of G1? How many edges are there?
4.
4.
What is length of G2?
3.
3. 3 odd. Okay. Therefore, this is called odd cycle. Therefore, this is called odd cycle. And 4 is even. Therefore, this is called even cycle. Is it okay? Okay. So, can you say that cycle, okay, is a special case of trial, closed trial, and which is a special case of closed work? Okay. And can you say that I think it should be erased because trial contains vertices may be repeated. No? So cycle is a special case of closed work only. And the path, okay, path is a special case of trial. And trial is a special case of work. Is that fine? And even cycle, odd cycle. Okay. Okay. So previously we talked about adjacent vertices. Okay. Now what do you mean by connected vertices? May I proceed?
Yes, sir.
Okay. So what do you mean by connected vertices? When do you say two U and V are connected?
There can be a walk from one vertex to any other vertex in the graph, sir.
Connected vertices I am telling. I'm not asking connected graph.
There is a multiple paths for vertices.
So what do you mean by two vertices are connected? That means there is a walk between those two vertices. If there is no walk, then that is said to be they are not connected. Okay, they are disconnected. So can you tell me which are disconnected?
U6, sir.
Cannot say with one vertex.
Yeah, U1
U1,
and
U6.
U6.
Or you can say U6 is disconnected with every other vertex.
Yes, sir.
Am I right? So U5, U6 are disconnected because there is no walk. U4, U6 are disconnected because there is no walk. U1, U6 are disconnected because there is no walk. There is no way reaching from U1 to U6. Whereas U1, U5 are connected because there is a walk. There can be several walks. I can walk like this, or I can walk like this, or I can walk like this. So if you can find out at least one walk from one vertex to another vertex, then that is said to be the then they are said to be connected. So what do you mean by connected graph?
If there is.
If there is a walk between any two vertices. Otherwise, it is said to be disconnected. Am I right? That means a graph is said to be connected if any pair of distinct vertices are connected. Okay, so something like this. Can I write like this? V1, V2, V3, V4, V5. Is this connected graph or disconnected graph?
Connected graphs.
So you take any two vertices. There is a walk between V1 to Vi. Therefore, it is a connected graph. Any two vertices are connected. Therefore, it is a connected graph. Okay. So a disconnected graph will have components where each component is a connected graph. Okay, this is a connected graph having one component. This is a disconnected graph having two components. Can you see that? This is one component. This is another component. This itself is a graph, connected graph. This itself is a connected graph. Or I can have a disconnected graph like this. U7. Okay, my graph is this whole thing. My graph consisting of 7 vertices. Is this connected or disconnected? It is disconnected because there is a pair of vertices which are not connected, but it is having two components. Do you see? Where each component is a connected graph. This is a connected graph, this is a connected graph. Is that right? Similarly, my graph can be like this. U8, U9, U10. Okay. Again, this whole thing, graph consisting of 10 vertices is disconnected, but this disconnected graph is having 3 components where each component is a connected graph. Can you see that? If I join like this, how many components are there in this graph?
2.
2. Okay, so this is one component, this is one component, this is another component. Is that okay? Now, what do you mean by distance between two vertices? Distance between two vertices is the length of the shortest path. Length of the shortest path u comma v. There can be several paths from u to v, and each path will have length. Among all those paths, the length of the path which is having minimum length is called the distance. And if they are not connected, okay, then the length of the path we call it as infinity. If u and v are not connected or disconnected. Okay, so in this graph, let us say what can be distance from u1 to u1 to u9? Can you tell me?
4, sir.
Distance is the minimum number of edges, minimum number of edges that is taken to reach, right? So 1, 2, 3, 4. Another path is 1, 2, 3, 4. I think another path is 1, 2, 3, 4, 5. This is another path 1, 2, 3, 4, 5. 5 path length. So that path is having length 5, but this path is having length 4 only. Therefore, we say the distance is 4. If I say what is the distance from u1 to u6?
Infinity, sir.
U6. It is infinity because these two are not connected. These two are not connected. U1, U6 are not connected. Therefore, the distance between U1 and U6 is infinity. Is it okay? Shall I proceed?
Sir,
Oh, tell me.
when we use D, like
Hmm.
since degree also has D of 2 vertices.
That is D for one vertex, right? But here we are using D
Oh,
for
got it, sir.
2 vertices, pair
Yes.
of vertices. Okay. So if you have any confusion, there you can write DEG also. Then that is precise, right? That means
Yes,
to
sir.
say degree. Okay. So either we'll write like this or degree of U equal to 2. Okay. May I proceed? So next topic is, so you understood what is walk, what is trial. Okay, so walk is a sequence of vertices and edges where edge is where edge is incident with its neighboring vertices. Every edge is incident with the neighboring vertices. Okay, trial is a walk in which all edges are distinct. Okay, and path is a trial in which all vertices are distinct. When all vertices are distinct, automatically all edges are also distinct. Okay, so every path is a trial, every trial is a walk. And what is cycle? Cycle is nothing but a closed path. Okay, it is a path except for initial and vertex and terminal vertex. Okay, uh, if initial vertex and terminal vertex are coinciding in a path, then that is said to be a cycle. And this cycle can be classified as even cycle and odd cycle based on the length of the cycle. Length of the cycle is the number of edges in that cycle. Okay, so odd number of edges, odd cycle; even number of edges, even cycle. Okay, so this cycles we are denoted with generally we denote with Cn. Okay, Cn with n edges. Okay, so every cycle will have exactly n edges. Do you agree? A cycle, this cycle is having 3 edges. This cycle is having 4 edges. That's why we generally denote with the Cn. Okay, so so this is an odd cycle. This is an even cycle. Okay. And what is wheel? Okay, if you are joining every element of a cycle with a vertex, then the so obtained graph is said to be a wheel. Okay, W1 is an adding in an additional vertex and connecting all with all other vertices. Okay, if you are connecting this with all other vertices in a cycle, that is said to be a wheel. So distance also we discussed. Okay, connected graph also we discussed. Connected graph means every pair of distinct pair of every vertices must be connected. Even if one pair of vertices are not connected, then the graph is said to be disconnected. A disconnected graph will have components where each component is a connected graph, connected subgraph. Distance we defined. Distance is nothing but the length of the shortest path joining two vertices is called the distance between those two vertices. Okay, and what is cut vertex and cut edge? Cut vertex means if you remove the vertex from the graph, if that graph becomes disconnected, then that is said to be a cut vertex. Okay, if it is making into more number of components, than the existing number of components, that is said to be a cut vertex. So in this you see, if I remove this, there are two components, that becomes a two components, therefore it is a cut vertex. If I remove this, that becomes a cut vertex. Okay, whereas if I remove like this, can you tell me what is cut vertex here? Let us say let us take this graph. In this graph, which one is a cut vertex in this graph?
V4, sir.
V4. If I remove V4, then this becomes the number of components becoming increasing, therefore it is a cut vertex. Is there any other cut vertex? What happens if I remove V5? Is it a cut vertex?
No, sir.
No, sir.
No, because number of components remaining same. What about this? Is it a cut vertex?
Sir, V2.
Yes, V2 is a cut vertex. If I remove V2, then this becomes disconnected, therefore V2 is also a cut vertex. Is it okay? Now what is cut edge? Again, if you remove the edge, if that becomes disconnected or the number of components are increasing, then that is said to be cut edge. So in this V2, V4 are cut vertices. What about V1? Is it a cut vertex?
No,
Even
sir.
if no, so only V2, V4 are cut vertices. What about cut edges? Which are cut edges? Let me denote these edges with these numbers. Letters here. Let us say A, B, C, D, E. Which edges are cut edges?
D and E, sir.
If I remove D, then this becomes disconnected. Therefore, components are increasing. D is a cut edge. What about E? E also cut edge, no? If I remove E, then V4 and V5 are disconnected, right? Am I right? Therefore, E also cut edge. Whereas if I draw like this, then even if you remove E, it remains the same. Therefore, it will not be a cut edge. This is not 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 a cut edge. So only D is the cut edge. Am I right?
Sir, D also won't be the cut edge, no, sir?
Yes,
D
sir.
is not a cut edge. Yes, because it is connected, right? Yes, this is not a connect. Only E. If this is the case, this is the case, only E will be the cut edge. Am I right?
E and D will be the cut edge, sir.
Okay. If I remove this, let me draw this. This becoming disconnected, no? Correct. These two are disconnected. Therefore, D is a cut edge. Even if I remove this, these two are disconnected. Therefore, E is also cut edge. But whereas if I remove this, nothing is happening. Therefore, it is not a cut edge. Is it clear?
Yes, sir.
Right. So that's about cut vertices and cut edges. We'll come back to this point when we are discussing trees. What is weighted graph? It is a graph where we assign some weight to each edge. We assign a weight to each edge. It's like the distance from one place to another place. Let us say there is a 50 kilometers. Okay, so that distance we may call it as weight. Okay, so weighted graph is a graph where there is a function from edge set to the set of real numbers. In fact, we denote with R plus. Okay, so if you are assigning some weights to each of the edges, okay, then we may call it as a weighted graph. Okay, so if I write some 10, 3, 6, 4, they are not the edge names. They are not the edge names, but we are assigning some weights to these edges. Okay, so something like if I am calling this as edge E1, if I am calling this as edge E2, edge E3, and edge E4, so what I am associating, W of E1 is equal to 10, W of E2 is equal to 3, W of E3 W of E3 equal to 6, W of E4 equal to 4. Okay, such a mapping. Okay, you may call it as a weight function. So if you are assigning weights to a graph, that resultant graph is said to be a weighted graph. Now, obviously, it is a very important concept. Okay, because you may want to find out the shortest distance between two nodes. Right? If you want to go to some tourist place and by a car or something, okay, obviously we'll see Google Maps, right, and see which path is the shortest path to go there, right? So connect and uh, there are several algorithms. There are called greedy algorithms. Okay, greedy algorithms are the ones which gives the minimum weight. Okay, minimum weight or minimum length. Okay, if you want to get an optimum values or minimum values through an algorithms, they are called greedy algorithms. Okay, so then so that is given by a famous algorithm called discross algorithm. Okay, so this algorithm provides distance from one vertex to all the other, shortest distance from one vertex to all other vertices in the same graph. Okay, it tells how to compute the shortest distance from one node to all the remaining nodes in the graph. Okay, so I'll come back to this bipartite graph. Okay, so what is this discross algorithm? I will demonstrate with an example. Okay, so okay, so I think today I'll discuss up to this, and in tomorrow's class I may start with the trees concept. Okay, okay, so what is okay, okay, so what is our this thing algorithm? So what is the input and what is the output? Okay, so input is a you also may write in your notes. Okay, weighted graph E comma W. Okay, the ordered pairs graph and the function. Okay, we will together we may call it as a weighted graph. Okay, okay, and a vertex you may call it as U naught. Okay, U naught. Every time it may be difficult for me to write it in a subscript, so I'll just write it as U0. U0 is nothing but U subscript 0, U naught. You write like that. Okay. So that is the input. What is the output you want? Weighted distance from U naught to every other vertex. U naught to every other vertex in G. Weighted distance from U naught to every vertex in G. Okay. So what is the so what do? We start with U naught. Okay, we will be giving some initializations. We'll be giving some initializations. I'm thinking whether to write the algorithm or demonstrate the algorithm. Okay, let me write down the algorithm. Okay, then you can refer that algorithm in case I'm doing any mistake here. Okay. Okay. So let me draw the graph then first. Okay, so I'm having a graph like this. Let us say graph like this. Okay, you may call this as a network. Okay, so V1, let us say V2, let us say V3, let us say V4, V5, and V6. Okay, so how this network is connected? V1 to V2, V2 to V3, V4, V4 to V6, V1 to V3, V3 to V5, V5 to V6, V2 to V3, and V4 to V5, and V2 to V5, V2 to V5. Okay, so the graph. Okay, so the weights are assigned like this: 1, 5, 2, 2, 1. This is 2, 1, 3, 2. Okay, so this is a weighted graph. Okay, where we are assigning edges to we are assigning weights to every edge. Okay, it may be a distance of 500 kilometers. This may be a distance of 100 kilometers. This may be distance of 200 kilometers, like this. We may assume like that. Okay, so then what is that algorithm? First we'll see the algorithm, and so write down the algorithm, copy the algorithm. Okay, so let me write down the algorithm. It is having few steps. Then I will we shall apply, because even if you miss some point in the algorithm, okay, you may not get the correct output. Okay, so step one is initialization. Okay, first you assign the initial from which vertex you want the distance, that the length you assign it as. So in this case, because I'm using v1, let me call it as we call it as v1. Okay, so in this case okay, you may initialize. Okay, you may initialize you may start with okay, sorry. Okay, so you want to start with, so with which vertex you want to start with, that you may call it as u0. Okay, so I may want to start with v1, or I may want to start with v6, or I may want to start with v5. I may want to find out the distance from v5 to all other vertices. What kind of distance? Distance itself mean to say that the shortest distance. Okay, so what is the resultant? Okay, so whatever the vertex you want to start with, that you call it as u0. Okay, so here I am selecting u0 as v1. Okay, so let us so while implementing the algorithm, we'll say what is u0. Okay, u0 can be v1. Okay, so for the time being, let us say that you are starting with some initial vertex, say it as u0. You assign L of u0 equal to 0. Okay, and assign infinity to all other vertices in the graph. Okay, for all v belongs to vertex set minus u0, singleton u0. Okay, so this is your first step. What is step 2? Okay, so you form a set called s0 equal to u0. Form a set called s0 equal to u0 with iteration number I equal to 0. With iteration number I equal to 0. In step 2, for every write down one, for every v belongs to vertex set minus Si. Si is this kind of set. Okay. Do the following things. First one, assign L of V value as minimum of L of V, comma L of Ui plus weight sum of the weights. Okay, now it is not about the distance. You have to find out the weight of the edges which are connecting Ui and V. Okay, and that should happen for all Ui belongs to Si. For all Ui belongs to Si. Second point is compute minimum of all those VIs. Compute L of Vi or L of V such that V belongs to V minus Si. C. Okay. Let Ui plus 1 be the vertex. Let Ui plus 1 be the vertex for which minimum is obtained. Minimum is obtained in the point B. Okay. Then define Si plus 1. Si plus 1 equal to Si union Ui. Ui plus 1. Okay. And what is step 3? Step 3. If I equal to nu minus 1. What is nu? Nu is the number of vertices. Where nu is the order of V. Okay, then stop. Otherwise, or else, go to step 2. Go to step 2 with Si plus 1. Go to step 2 with the Si plus 1. This is the algorithm. Okay. So, what is this? How this algorithm? How to implement this algorithm to find out the shortest distance from given vertex to every other vertex? We'll see now. Just write down this in your notes and just recall the point as and when I discuss the problem. Did you copy? Shall I scroll up or is it fine? Did you copy? May I proceed?
Yes, sir.
Right. So now I will copy this figure in the next page and implement this one. Okay. So draw. Okay. We'll see. Control V. So I'm going to prepare a table. Now I want to start with V1. Now I want to find out the shortest distance from V1 to every other vertex. Okay. So what is my initialization? What do you mean by U0 initially?
V1, sir.
V1. So I'm calling it as U0. And what is L of U0 I am giving? 0. Do you agree? Okay. So what is your S0 initially? S0 is initially singleton U0. What about L of Ui? L of V? For all the remaining vertices, I am assigning it to infinity. Is it clear? For all,
Yes, sir.
for all V belongs to set of vertex set minus S0. Okay. Now you prepare a table. Okay. So I will prepare a table here. Okay. So what is a table? Index number I, the set Si. Okay. So minimum of L of Vi such that Vi belongs to vertex set minus Si Ui plus 1 and Si plus 1. Okay. So index number 0. Initially we selected U0 only. Am I right? Initially we selected U0. I assigned U0 to S0. Okay. Now remaining vertices are now, as of now, they're all infinity. Okay. L of V2 is assigned as infinity. L of V3 is assigned as infinity. L of V4 infinity. L of V5 infinity. L of V6 infinity. Okay. So among all these vertices, okay, you find out the vertex which is having shortest distance from every vertex of this current set Si. As of now, Si is containing only U0. So which vertex is having less weight, minimum weight, when compared to U0? V2 to U0 is, what is the weight?
1, sir.
1. What is U0 to V3? 5. And what is U0 to V5? 7. Okay, if you want to go to V5, obviously you have to cross V3. That means it is sufficient to check these two only, because remaining distances or weights will be more than these two weights. So minimum weight as for a singleton vertex exists only between these two. So which one I have to consider? V2 or V3? V2. So what is that length? Or so now what is this distance? For the time being, call it as distance. Actually it is not distance, it is actually weight. Okay. So what is this? Or you may assign distance to the edges also, doesn't matter. Okay. No. So what is this one? No. V1 to V2, what is the weight? 1. Okay. So 1 is the minimum of all the other distances. Okay. So how many? So 1 is actually what? Minimum of, let me show you. Minimum of, so 1, 5, and V1 to V5 is 7. V1 to V4, it can be 3, like that. Okay. Actually, okay, that's it. So that is the minimal length 1. Okay. So the distance from, so I am calling this as so what is the next vertex? What is this one? U. This is U. This is U. So what is my next vertex? Ui is over. Ui is V1. What is Ui plus 1? V2. Okay. So that means what? This is U1. Now what is Si plus 1? Union of these two. union of these two. This I am calling it as U1, right? So what is this? This is nothing but U0 comma U1. So for the next iteration, my S set is this one, U0 and U1. Okay. So now you are having these two. Okay. What is L of U1? Let me write here. Okay. Let me write here. L of U0 is over. L of U0 is 0. L of U1. L of U1 is written as 1. And now remaining vertices are having infinite length. Remaining vertices are having infinite length. Okay. Now you look at the remaining vertices. The remaining vertices are, so U1 is nothing but V2. Remember this. So remaining vertices are V3, V4, V5, V6. Among all these vertices, okay, which vertex is nearest to these two? V3.
V3, sir.
Okay. See, that should be, see the algorithm once. That is not this step. This one you have to see. Minimum of L of V, comma, L of Ui plus walk from Ui to V. That one you have to see. That means current weight plus walk from V to Ui. Okay. So that means to say, so if I want to consider 3, V3. So what is V2 to V3? 2. And this 2 you have to add to L of U1. So 2 plus 1 is how much? 3. Is it okay? In this way it is 3. But in this way 5. What is L of U0 already? 0. 5 plus 0 is 5. So which one is minimum? Or you take this one. V4. What is V2 to V4? 2. Already what is V2 is having? Or U1 is having 1. So 2 plus 1 is how much?
3.
3. But here 2 plus 2 is 2 plus 1 is also 3. So that means you can select V4 or V3 as your next vertex. Or what about this? V5? Is this minimum?
Yes, sir. 2.
See, this is 1 and L of U1 is already 1. 1 plus 1 is 2. I think this is the minimum, not V4 and V5. Or you take this vertex. 1 and 1 plus L of V4 we don't know. Already it is infinity as of now. So this is not the right candidate. This is not the right candidate. This is not the right candidate. So what is my next vertex in this graph? V5.
V5.
Okay. So V5. What is that distance? 1 plus 1 is 2. Okay. So so I'm calling this as U2. I'm calling this as U2. Okay. And the length is length of U2. Length of U2 is equal to what? 1 plus already the previous walk. Walk from these two vertices plus and the previous walk. Okay. So that is 1 plus 1, 2. Whereas if you take like this, if you take this vertex 1 plus 1 2, 2 plus 0 2, that is also okay, fine. Okay, but if you take like this 5 plus 2 7, 7 plus 0 7, okay, that is not the case. So minimum of 2 comma 7 is 2 only. So my distance from minimum distance is going to be 2 and by next vertex is going to be U2. U2, therefore your new set is going to be U0, U1 and U2. Okay, now go to the next iteration. What is the next iteration? U0, U1, U2. Now your S containing these three vertices. S containing U0, U1 and U2. And remaining vertices are V3, V4, V6. Now take each vertex, compute the distance from V3 to the remaining vertices. Okay, and how you are computing V3 to U0 distance plus the weight already, or weight is already assigned to that vertex. That also you have to add. So V3 to U0, how much? 5 plus U0 weight is 0. 5 plus 0, 5. And V3 to V2, 2. And 2 plus V2 weight is 1. This is 3. And V4 to V2 is 2. 2 plus V2 weight is U1 weight is 1, 3. So these two are having same weights, 3. Whereas this is already over and this is already far. So you can select V3 or V4 in between these two. Which one you want to select as the next U? V3 or V4? You need to add these two to the walk length from the vertex to the every element of this set S. Okay. So what is this? Shall I select V3 as the next element? If I select V3 as the next element, I have to call this as U3. Am I right?
Yes, sir.
Then what is its weight? Its weight is going to be
3.
2 plus weight of U1. Weight of U1 is 1. So 2 plus 1 is 3. So this is 3. So next vertex is U3. So new set is U0, U1, U2 and U3. Now go to the next iteration. So U0, U1, U2, U3. And what is length of U3? Length of U3 I have to copy here. Length of U3 has to be 3. Length of U3 is 3 already. Okay. Now next one is obviously this one U4, 2 plus 1. Okay. So I will call this as U4. So because this is shortest, this is V4 is nearest to V2 and V2 weight is already U1. So 2 plus 1 is 3. That is minimum when compared to all other vertices. So I will call this as U4. So what is U4? Again, its distance is 3. 2 plus length of U1 or weight of U1. Okay, so this is also 3. So my next vertex is U4. U4 is nothing but the vertex V4. So my new set is U0, U1, U2, U3 and U4. Okay, now iteration number 4. Okay, iteration number 4. Now U0, U1, U2, U3 and U4. Okay, now what is the next vertex you have to see? What vertex is remaining? Only this vertex. Okay, so this vertex is nearest to V5 or V4?
V4.
V4. But what is so 1 plus weight of U4? What is weight of U4? Did I write? I didn't write here. Let me copy this. So length of U4 is 3. So 1 plus 3. 1 plus weight of U4 is 3. 3 plus 1 is 4. Whereas if you take like this, 2. 2 plus weight of U2. What is weight of U2? 2. 2 plus 2 is 4. 4 is more than this. This is also 4, I think, right?
Yes, sir.
So any edge you can take. That means you are taking all the things. So that means what? So that the weight, what will be that weight length? 4. That weight length is 4. So it is going to be U6. Okay. So this is nothing but U0, U1, U2, U3, U4 and this is U5. Sorry. This is U5. So this I am calling it as U5. So what is length of U5 means? 4. Length of U5 means 4. Okay. So this is 4 and this is U5. So we explored all the things, right? So 1, 2, 3, 4, 5, 6. How many vertices? 1, 2, 3, 4, 5, 6 vertices. Okay, and now you see, you from u0 you tell me any vertex. I can tell the distance here from this table. Okay, suppose you want the shortest distance from u0 to u4. What is the shortest distance? You can see here 3. And what is the shortest distance from u0 to u5? That is 4. You can see 4. 1 plus 2 plus 1, 4. There exists a shortest path of minimum weight. Similarly, if you want the shortest distance from u0 to u5, what is the weight? u0 to u5, u0 to, here in this case u2. So what is L of u2? 2. What is that 2? 1, 1. 1 plus 1, 2. Is it okay? So these are the shortest distances or shortest minimum weights from one vertex to any other vertex in the graph. Is it clear? So that is how we can find out the minimum, the shortest distance from one node to every other node in the graph. Okay, so you try to implement this algorithm for another graph. Okay, I shall post it because vertex names are not given here. So I shall post one problem as a homework. You implement a discuss algorithm to that. Okay, so after that we'll go to what is bipartite graph and trees. Okay. Let me complete this bipartite graph. Bipartite graph is nothing but if you partition the vertex set into two sets such that no two vertices are adjacent in the first set, no two vertices are adjacent in the second set. That means there should not be any edge between any two vertices of the first vertex set. There should not be any edge between any two vertices of the second set. There may be edge connecting these two vertices, or there may not be edge. It doesn't matter, but these two should not be adjacent. None of these two should be adjacent. Such a graph is said to be bipartite graph. Okay, and what do you mean by complete bipartite graph? Whereas every vertex is adjacent to every other vertex in the other vertex set. This is adjacent to every other vertex, and these two are not adjacent. This is adjacent to every other vertex. Okay, these two are not adjacent. This is adjacent to every other vertex. This is adjacent to every other vertex. Okay, so this is one set. This is another vertex set. This is adjacent to another vertex, and no two vertices are adjacent. So this is a complete bipartite. Here also, no two in this set are adjacent. No two in this set are adjacent, and there is a edge between every vertex of this graph to every other vertex of this graph. Therefore, this is called as a complete bipartite graph. So this may be called as K23, where two denotes the number of vertices in the first graph, 3 denotes the number of vertices in the second graph. Similarly, K33, number of vertices in the first graph, number of vertices in the second graph, and there is an edge between every pair of vertices from one vertex set to another vertex set. Is it clear? Bipartite graph and complete bipartite graph.
No, sir.
Okay, let us draw one graph.
Sir,
Tell me.
sir, the last three nodes are not connected, no, sir.
This one.
The before one, sir. Even this one also.
This one. Tell me.
You said that every node should be connected with every vertex should be connected, no, sir.
See, let me draw one graph. Let me show you. So let me draw a graph like this. Let us say V1, V2, V3, V4. Okay. So what is your vertex set? V1, V2, V3, V4. Am I right? What are edges? Let us say A, B, C, D. Now you partition this vertex set into two sets. Okay, what do you mean by partition? Intersection must be partition means what? V1 intersection V2 must be empty, and V1 union V2 must be the whole set. Such a sets are considered to be partition sets. Okay, I can partition like V1 as one set, V2, V3, V4 as another set, or V1, V2, V1, V2 is another set, V3, V4 as another set, or V1, V3 is one set, V2, V4 are another set. Like that, I can make several partitions. Partition means make into two sets, which does not share any common point, and their union must be the whole set. Now, how can I call this as a bipartite graph or not? Okay, or can I make this into a bipartite graph? V1, V2. Okay, so can I include V1 here? Sorry, I'm using the same notations. I'm sorry for it. Let me call it as U1, U2. U1, U2, U3, U4. So let me call it as U1 here. Let me put U1 here. Let me put U3 here. Let me put U2 here. Let me put U4 here. Now, is there any edge between U1 and U3? Is there any edge between U1 and U3?
No.
No. Is there any edge between U2 and U4? Are these two adjacent? No. Now join the edges. Okay, what is A? A is connecting U1 and U2. What is U1 and U2? So like this. And B is connecting U2 and U3. U2 and U3. And C is connecting U3 and U4. Okay, so this is A. This is B. And C is connecting U3 and U4. Okay, C is connecting U3 and U4. Therefore, this is C. And D is connecting U4 and U1. D is connecting U4 and U1. So this is D. So this is a bipartite graph. Okay. So because this is a bipartite, because I partition the vertex set into two sets such that no two vertices in the first set are adjacent, no two vertices in the second set are adjacent, and whatever the edge is there, that edge has one end in the first set, the other end in the second set. If at all there is an edge, one end should belong to the first set, the other end should belong to the second set. If that is the case, we say it is a bipartite graph. Is it okay? If I draw a graph like this, suppose if this is my graph, can you make a bipartite graph from this? Let me draw separately. Suppose if it is like this, U1, U2, U3, U4. Okay, so you have to partition into two sets such that no two vertices in the first set are adjacent. So let us say if I am putting U1 here, which one I should not put here? Let me call this as V1. Sorry. Let me call it as V1. Let me call it as V2. So which vertices I cannot put here? Can I put U2 here?
No, sir.
Can I put U3 here?
No, sir.
No.
Can I put U4 here?
No.
Because they're all adjacent. So remaining three has to be here only. You cannot put any vertex here. Is that clear? Now, if the remaining vertices are to put here, that means to say that this is U2, this is U2, U3, and U4. So there is an edge from U1 to U2. I agree. But there are edges from U2 to U3 also. No, see here.
Yes, sir.
That should not happen. In a bipartite graph, no two vertices must be adjacent. Okay, can you construct like that? You cannot form a bipartite graph from this. Am I right? So if at all there is a bipartite graph, or if I am giving the graph like this, so instead of drawing the graph like this, I can draw the graph like this only. So by simply I can say this as bipartite graph. This is a bipartite graph because these two are not adjacent. These two are not adjacent. Like this is a bipartite. So now do you understand how these two are bipartites? How this is bipartite? No two vertices are adjacent. If at all there is an edge, one end of the edge is belong to the first set, vertex set, another end belonging to the second vertex. Such a graph is said to be bipartite graph. Is it okay? Please tell me. See, I'm not telling how to identify whether a given graph is bipartite or not. Okay. If a graph, okay, so if a graph is given, okay, where some set of vertices belong to another set of vertices belong to another set. Okay, no two vertices are adjacent, then you can call it as a bipartite graph. I can construct several bipartite graphs, right? 1, 2, 3. 1, 2. Okay, what is one bipartite graph? Like this. This is one bipartite graph. This is another bipartite graph. This is another bipartite graph. As long as you don't give edges between these two vertices, this becomes a bipartite graph. Is it clear? Please respond.
Yes, sir.
Right. So, I will stop the class now. In tomorrow's class, we'll discuss about trees and their properties and different kinds of trees. Okay.